Hello everyone, today we're going to go over the chain rule with some examples and using some better notation. And I especially prefer this notation for doing computations with the chain rule. Over here we have Leibniz's notation as well as Lagrange's notation, which apparently according to Wikipedia was done first by Euler and popularized by Lagrange. So we have Leibniz's notation on the top over here, and then we have Lagrange's notation over here. And I really prefer Leibniz's notation, especially for computations. And I just wanted to show a couple examples using Leibniz's notation and how I think it breaks down the process a little bit further in case you wanted to take more steps. So over here we have an example of the derivative of the square root of 2x plus 1 with respect to x. So typically you will not see this process be done very extensively where you explicitly define some inside function. So in this case I'll do it explicitly. So I'll say let u equal 2x plus 1. So then our derivative is going to be d by dx of, or even if you wanted to like break it down further, you could say let y equal the square root of 2x plus 1. So then you can rewrite y as the square root of u. So then you have the derivative from above. That's going to be equal to dy by dx, because this is over here on the inside is u, and then over here you have the square root of this, which is what we call y. So we have dy by dx, which according to the chain rule we can break it down as dy by du times du by dx. And we can resubstitute what we had for y, which we're going to put in terms of u so that we can compute this derivative. And then over here du by dx we'll substitute in our value for u in terms of x. So du, which we put it as the square root of 2x plus 1 with respect to x. So then if we wanted to put this down a little bit slowlier, we do u to the 1/2 for square root of u. And then sorry, u should be just 2x plus 1 over here, not the square root of 2x plus 1. So then we have d 2x plus 1 by dx. So then the next line we'll have 1/2 u to the power of negative 1/2 times the derivative of 2x plus 1 with respect to x is just 2. The halves cancel out, so you're just left with u to the negative 1/2, which is going to be u 1 over u to the half. Which is 1 over the square root of u, which is 1 over the square root of 2x plus 1 if we just substitute in our value for u over here. Next, I'm going to show this entire process again, but I won't be substituting u or defining y or anything else like that explicitly. I'll just be computing the derivative. So I'll be kind of grouping all of those into u and x and y in my head. So here we're gonna take the derivative of the square root of 2x plus 1 with respect to whatever that inside thing is, which we called u before. So I'm just gonna put 2x plus 1 here instead of explicitly writing u, times this inside function, which we called u before, with respect to x. So over here we treat this 2x plus 1 as one entire clump like we did last time and called it u. And then we say, maybe explicitly we want to put 2x plus 1 to the power of 1/2 if that's a little bit easier for us to deal with, times this derivative we can already just simplify it to 2, compute it to 2. So over here we get 1/2 times 2x plus 1 to the power of negative 1/2 times 2. Now 1/2 and 2 multiply together to get 1, so you just get 2x plus 1 to the negative 1/2. That gives us 1 over 2x plus 1 to the 1/2, which gives us 1 over the square root of 2x plus 1. So in both cases you get the same answer, but one we explicitly define what u is, what y is, and then the next one we don't. So another example over here, the derivative of 2x plus 7 all to the power of 9 with respect to x. Again, if we wanted to explicitly say let u equal 2x plus 7, then you can say let u equal 2x plus 7, and then we can say let y equal u to the 9, which is the same thing as 2x plus 7 to the power of 9. So then our derivative over here, that's going to be equal to d by dx of, or dy by dx, since this is just u to the power of 9. Then our chain rule says we can do dy by du times du by dx. Then we can substitute in y in terms of u, so we have d times the derivative of u to the power of 9 with respect to u times, and then over here we can substitute in our value for u in terms of x, so 2x plus 7 to the power of 9 with respect to x. And then over here our derivative is 9u to the power of 8 times 9, oh no, sorry, this is just this inside part, which is just u, which is going to be 2. And then over here we substitute in our value for u, 9, 2x plus 7 to the 8 times 2, which gives us 18, 2x plus 7 to the power of 8. And again, on the right side, we can do this without defining u or anything else like that, if we are able to visually clump these things together as some inside function. And you can kind of see these chains are kind of linking, where you have your outside your parent function, and you have an inside function, and that chains over here this exact same thing. And then again you go to the next inside function, which here just happens to be x. So now we do this derivative times 2, which gives us 18, 2x plus 7 to the power of 8. So again, same answer, just taking a little bit fewer steps here and skipping a couple more steps.